the previous video, we discussed Lorentz transformations, length contraction, and time dilation. T bar equals T minus Vx over square root of 1 minus V squared. X bar equals X minus Vt over square root of 1 minus V squared. In this video, we will discuss the concept of proper time. Imagine a clock in space and imagine a moving observer A. This is his frame of reference, X and T. This is the trajectory of the clock in his reference frame, X equals Vt. Or let's call it X naught equals 0. X naught being the line of simultaneity of the clock to itself. Now, this length means the time read by the clock, or the time of the clock in relation to its own frame of reference. Now imagine another observer B, moving in velocity capital V. This is her frame of reference, capital X and capital T. No matter what the speeds of moving observers are, or no matter such moving observers exist or not, the time read by the clock is the time read by the clock. No matter what the frame of reference you use to calculate it, time read by the clock to itself is the same. So let's calculate a relationship between the clock and the frame of reference independent of the moving velocity. If this time interval is t naught, then by Lorentz transformations, x bar equals x minus vt over square root of 1 minus v squared. T bar is t naught and x naught is 0 along this line. So 0 equals x minus vt. So v is x over t. T bar is t minus vx over square root of 1 minus v squared. So t bar becomes t naught. T naught equals t minus v. V is x over t times x divided by square root of 1 minus v squared. V is x over t squared. So t squared minus x squared divided by t, and in the denominator we will take t squared out. So when you take it out of the square root, it becomes t. So t squared minus x squared square root divided by t. T cancels off. T squared minus x squared divided by square root of t squared minus x squared. So t naught is square root of t squared minus x squared. In other words, t naught squared equals t squared minus x squared. So whatever the coordinate system you consider, regardless of its velocity, t naught squared equals t squared minus x squared. T naught is invariant. Similarly, let's consider a straightened up tape in space. This is a moving observer, A. His velocity is v. And this is the trajectory of simultaneity of the tape in his frame of reference. In other words, this is the length of the tape measured in its own reference frame, or the length of the tape to itself. This is t equals Vx, or t not equals 0. This is another moving observer, and this is her frame of reference. Once again, no matter what the frame of reference you use to calculate it, or whether such frames of references exist or not, the length of the tape measured is the length of the tape. The length of the tape measured in the tape's reference frame is the same, because it is the measurement of the tape to itself. Let's apply Lorentz transformations to this. Here t equals t naught and is 0. T bar equals t minus Vx over square root of 1 minus V squared. So t bar is t naught and it is 0. So 0 equals t minus Vx. So V is t over x. X bar equals x minus Vt over 1 minus V squared. X bar is x naught. So x naught equals x minus Vt. V is t over x divided by square root of 1 minus V squared. V squared is t divided by x squared. So x squared minus t squared divided by x. The denominator is, we'll take x squared out, so it becomes x. X squared minus t squared square root divided by x. So x cancels off. So x squared minus t squared divided by square root of x squared minus t squared. So x naught is square root of x squared minus t squared. In other words, x naught squared is x squared minus t squared. So whatever the coordinate system you use to calculate, regardless of its velocity, x naught squared equals x squared minus t squared. Now look at the symmetricity of these two. T naught squared equals t squared minus x squared. X naught squared equals x squared minus t squared. They both are similar to the difference between t squared and x squared. So in a reference frame, x, t, this is the line of a light ray. T naught refers to a point in space-time above the light ray, and T naught is the distance to this point from the origin. X naught refers to a point in space-time below the light ray, and x naught is the distance to this point from the origin. Since they both refer to the distance to a point in space-time from the origin, let's call it tau. So in general, tau squared equals t squared minus x squared. Tau is called the space-time interval. It is also called the proper time. Notice when t naught is bigger than x naught, this point is in this region above the light ray. So the line connecting this point to the origin is a possible time axis, a line of existence. So if t naught is bigger than x naught, this trajectory is said to be time-like. When t naught is smaller than x naught, then this point is in this region, below the light ray. So the line connecting this point to origin is a possible length axis, a line of simultaneity. So if t naught is smaller than x naught, this trajectory is said to be space-like. What happens when t naught is equal to x naught? Then this is the light ray. When t naught is equal to x naught, tau squared equals 0. Therefore, when you travel in the speed of light, time does not pass. What about the other dimensions of space? Let's imagine a point in one coordinate system, x, y, and a point. Let's imagine another rotated coordinate system, x bar, y bar, and time is the same. In this new coordinate system, x squared equals x bar squared plus y bar squared. If you consider a rotated coordinate system in other direction also, in general, x squared must be equal to x bar squared plus y bar squared plus z bar squared. So in very general terms, tau squared must be equal to t squared minus x squared plus y squared plus z squared. Let's consider a coordinate system, x and t. This is a light ray, x equals t. And this is another one, x equals minus t. If you bring other axes of space here, what happens? Let's consider y-axis only. When you take ty plane, this is the light ray, t equals y. This is the other light ray, t equals minus y. So in general, the light rays form a cone like this. This is called the future light cone. Points on this cone are the points to which a light ray can be sent from the origin. This is the past light cone. Points on this cone are the points from which light ray can be sent to the origin. The region inside these cones is the time-like region. Region outside these cones is the space-like region. This is what you should generally know about the special theory of relativity. It alters your ordinary notions of space-time, present moment, and existence. But it goes much more beyond. It alters our notion of energy, momentum, and matter. To take you there, some elegant mathematical apparatus are required. We will explain them in the next video. In the next video, we will discuss about the Euler-Lagrange equation. This video series on relativity brings you a comprehensive understanding of the nature of time in terms of modern physics. The objective is to make you clearly see this conscious notion of time is an illusion. The notion of a past and a future and a present moment moving towards future. Why it is so important to know? It is because you are nothing else but the notion of time itself. When you see this time you see is an illusion, then this you that you see is an illusion. You that you are protecting, defending, and carrying forward is an illusion. It is the most important thing you are going to ever know. While this relativity video series provides you the physics knowledge, the Introspectum Stage 1 video series provides you the knowledge on axioms of conception. So we invite you to watch both. Subscribe to this video channel because this is going to be a complete course on the nature of time. You can download this lecture note from the link given below.